The Milky Way stretches across the night sky like a river of starlight, but behind its shimmering beauty lies secrets we're only beginning to unravel. From black holes that warp the fabric of space to ghostly signals with no obvious source, our galaxy is filled with puzzles that defy explanation. Some of these mysteries might hold the key to understanding the universe itself, while others could rewrite everything we thought we knew. Today, we're venturing into the unknown, counting down the 25 most baffling phenomena hiding right in our cosmic backyard. What you're about to discover might just leave you questioning reality. Somewhere in the depths of space, hidden behind the thick dust and stars of our own galaxy, an unseen force is pulling entire galaxies toward it, including our own. Scientists call it the Great Attractor, a gravitational mystery so powerful that it bends the motion of hundreds of thousands of galaxies like a cosmic puppet master. First discovered in the 1970s, this colossal anomaly sits in what astronomers call the zone of avoidance, a region so obscured by the Milky Way's dust and gas that optical telescopes struggle to see through it. Even though it's relatively close, just 250 million light-years away, its true nature remains shrouded in secrecy. Some theories suggest it could be a massive cluster of galaxies, while others propose something even stranger, like dark flow, a mysterious force tugging matter beyond the observable universe. But with so much still hidden from view, the Great Attractor keeps its secrets locked away, reminding us just how much we still have to learn about the forces shaping our cosmic neighborhood. One of the most compelling clues to solving the Great Attractor's riddle might lie even farther away, 650 million light-years beyond it, where the Shapley supercluster looms as the most massive concentration of galaxies ever found. Could this colossal structure, packed with tens of thousands of galaxies, be the true source of the gravitational pull we've been feeling? Some researchers think so, suggesting the Great Attractor itself might just be a waypoint in a far grander cosmic tug-of-war, with Shapley's immense gravity dragging everything toward it. But there's another, far stranger possibility. What if the force we're detecting isn't just from visible matter at all? Exotic forms of dark energy or hidden dimensions could be warping space in ways we don't yet understand. The good news is we might not have to wait much longer for answers. Cutting-edge projects like the Square Kilometre Array or SCAR will soon scan the skies with unprecedented sensitivity, peering through the zone of avoidance like never before. By mapping the faintest radio whispers of distant galaxies, this next-generation telescope could finally expose what's been pulling us and everything around us toward the unknown. Until then, the Great Attractor remains one of the Milky Way's most tantalizing mysteries, a reminder that even in our own cosmic backyard, the universe still has surprises up its sleeve. Rising from the heart of our galaxy like twin titans, two colossal bubbles of scorching gas stretch 25,000 light-years into space, one above the Milky Way's disk, one below. These aren't ordinary clouds, they're the Fermi Bubbles, blazing with gamma rays so intense they outshine the rest of the galaxy combined. When NASA's Fermi Gamma Ray Space Telescope unveiled them in 2010, astronomers were stunned how had something so massive, so energetic, remained hidden in plain sight. Packing the punch of 100,000 supernova, these structures defy logic, their origins etched in cosmic violence. The leading suspect, our galaxy's supermassive black hole, Sagittarius A. Imagine a sleeping giant stirring 4 million times the mass of our Sun, belching out jets of plasma in a cataclysmic outburst. Some researchers believe this monster awoke just a few million years ago, its feeding frenzy launching shockwaves that inflated the bubbles like cosmic balloons. Yet there's another culprit vying for explanation, a frenzy of star formation near the galactic center. If hundreds of massive stars were born and died in quick succession, their combined supernova could have pumped enough energy into space to carve these gargantuan structures. Here's where it gets even stranger. The bubble's edges glow with mysterious X-ray filaments, thread-like structures that resemble a vast celestial spiderweb. No one knows exactly what's creating them, but they hint at magnetic fields channeling particles at near-light speed. With every new observation, from radio waves to ultraviolet light, the Fermi bubbles refuse to fit neatly into any single theory. They're a testament to the raw power lurking in galactic cores, a reminder that even the Milky Way has explosive chapters in its history we're only now beginning to read. Future telescopes, like the upcoming Cherenkov Telescope Array, may finally settle the debate, peering deeper into these gamma-ray behemoths to uncover whether they were forged by a black hole's tantrum or a stellar fireworks show. Until then, they loom over our galaxy like spectral sentinels, whispering secrets about the chaos simmering at the heart of everything we call home. For 72 unforgettable seconds in the summer of 1977, the Big Ear Radio Telescope in Ohio picked up something extraordinary, a burst of radio waves so strong, so precisely tuned that the astronomer who discovered it scribbled, "Wow," in red ink across the printout. Decades later, that single word still defines one of space's most electrifying mysteries. The signal came from the constellation Sagittarius, blaring at exactly 1420 MHz, the frequency hydrogen naturally emits in space, a logical choice for any civilization trying to announce its presence. It was 1,000 times louder than background noise, matching all the hallmarks of an artificial transmission. And then, just as suddenly as it appeared, it vanished, never to repeat despite countless searches. Some have tried explaining it away. A passing comet, not likely. The signal's characteristics didn't match known comets in the area, nor would a natural object produce such a narrow, intense frequency. Satellite interference, impossible. Human technology at the time couldn't transmit at that strength. The truth is, no mundane explanation fits. That's why SETI scientists still chase similar signals today, scanning the skies with tools far more advanced than Big Ear. Projects like Breakthrough analyze millions of radio channels simultaneously, hunting for another wow, or better yet, one that repeats. The chilling possibility remains. We might have heard a cosmic hello, a one-time beacon from a civilization too distant or too brief to follow up. Or perhaps the signal was never meant for us at all, an interstellar broadcast sweeping past Earth by chance, like a ship's searchlight briefly illuminating a faraway shore. Whatever it was, its legacy endures as a haunting reminder that the universe is vast enough to hide countless secrets, and patient enough to let us wonder. If you've ever spun a ball on your fingertip, watching it wobble yet never fly apart, you've seen a hint of the Milky Way's greatest secret, the invisible hand keeping it all together. Meet our galaxy's dark matter halo, a vast, ghostly cocoon woven from material we can't see, touch, or even directly detect. Yet without it, the Milky Way would tear itself apart in a cosmic instant. Here's the staggering truth. Every star, every planet, every speck of dust you can see adds up to just 10% of our galaxy's mass. The rest, a mysterious substance whose gravity binds everything together, dark matter. We know it exists because stars orbit the galaxy's center far faster than visible matter alone should allow, like children whirling on a carousel that ought to fling them off, yet something unseen holds them tight. Some of the best evidence comes from gravitational lensing, nature's magnifying glass. When light from distant galaxies bends around our Milky Way, the distortion reveals hidden mass where no stars shine. Think of it like spotting footsteps in fresh snow, tracing a presence you never saw. But what is it? Leading theories suggest exotic particles like actions or dark photons, entities that barely interact with normal matter, slipping through our world like ghosts through walls. Experiments deep underground hunt for their faint whispers, while particle colliders attempt to manufacture them from pure energy. So far, the dark side of our galaxy remains elusive. Solving this riddle could rewrite physics itself. Is dark matter the glue of the cosmos or a sign we've misunderstood gravity entirely? Until we know, this invisible skeleton will keep holding our galaxy together in silent defiance, its secrets written in the spaces between the stars. The Milky Way isn't just a serene island of stars. It's a cosmic predator growing larger by feasting on smaller galaxies that stray too close. Right now, it's tearing apart the Sagittarius dwarf galaxy in a slow-motion act of destruction that's been unfolding for billions of years. Hubble's sharp eye has captured the aftermath, eerie rivers of stars wrenched from their original home and stretched into shimmering streams that wrap around our galaxy like celestial tinsel. This isn't some rare event, it's how galaxies evolve. Gravity's relentless pull bends and distorts smaller neighbors until they unravel, their stars scattered across the Milky Way's halo. Some astronomers compare it to a spider weaving its prey into a web, digesting it over eons, and Sagittarius dwarf isn't the first victim. The Gaia spacecraft has traced stellar fossils in our galaxy's outskirts, relics of past mergers that helped build the Milky Way into what it is today. But the most dramatic feast is yet to come. In about 4.5 billion years, Andromeda, our nearest galactic neighbor, will collide with us in a dazzling slow-motion crash. Computer simulations show the two galaxies tangling, their stars flung into new orbits as gravity reshapes them into a single, colossal structure. The sun will likely survive, but our night sky will transform into something unrecognizable, a canvas of newborn star clusters and tidal tails glowing with cosmic fire. What's startling is how abnormal this violence actually is. Without galactic cannibalism, the Milky Way would be smaller, dimmer, perhaps even lifeless, since mergers deliver fresh gas to spark new generations of stars. So while it might sound brutal, this devouring dance is part of what made our corner of the universe habitable. In the grand story of galaxies, destruction and creation are two sides of the same coin, and we're living proof. Stretching across the cosmos like a gaping wound in space, the Boötes void defies everything we know about how the universe should look. This immense spherical region, 330 million light-years wide, contains barely a handful of galaxies, making it one of the loneliest places imaginable. If the Milky Way sat at its center, we wouldn't have seen another galaxy until the 1960s. That's how empty this place truly is. Astronomers call it a supervoid, a cosmic desert where matter seems to have gone missing. In a universe teeming with galaxies clustered like glitter, the Boötes void is a baffling anomaly. Some speculate it could be the imprint of an unfathomably ancient collision between universes in the multiverse, or even evidence of advanced civilizations harvesting entire galaxies for energy. But the most plausible explanation might be even stranger. Just beyond this eerie emptiness lies the Hercules Corona Borealis Great Wall, a structure so massive it challenges the very laws of cosmology. Stretching 10 billion light-years, this filament of galaxies is the largest known object in existence, so vast it shouldn't exist under current theories. Could these two extremes be connected, one a barren void, the other an overcrowded metropolis of galaxies? Some scientists propose they're flip sides of the same coin, cosmic defects from the universe's birth, when quantum fluctuations froze into the fabric of space-time. Yet for all the theories, the Boötes void remains stubbornly silent. Unlike black holes or neutron stars, it doesn't emit radiation. Unlike dark matter, it doesn't bend light. It simply is a vast, indifferent nothingness that forces us to question whether we've truly mapped the universe's architecture. Future telescopes like the Vera Rubin Observatory may finally reveal if this void is a statistical fluke or a sign of something deeper lurking in the cosmic shadows. Until then, it stands as a haunting reminder that even emptiness can be a mystery. In the quiet darkness between the stars, the cosmos occasionally erupts with a scream, a flash of radio waves so intense it outshines entire galaxies in a fraction of a second. These are fast radio bursts, or FRB, and for years they seemed like distant enigmas flaring from galaxies billions of light years away. Then, in April 2020, everything changed. For the first time, one exploded inside the Milky Way, racing toward Earth from a bizarre object known as SGR 1935 plus 2154. This wasn't just any cosmic signal. Packed into mere milliseconds was as much energy as our Sun releases in 30 days. A staggering burst from a city-sized magnetar, a neutron star with a magnetic field a trillion times stronger than Earth. Picture a super-dense corpse of a dead star, spinning furiously while its unimaginable magnetism twists and snaps like rubber bands stretched to breaking point. When those magnetic fields finally recoil, they unleash quakes so violent they ripple spacetime itself, sparking FRBs detectable across the universe. Yet not everyone's convinced magnetars are the sole culprits. The precision of some FRBs, their crisp frequencies, their patterns, has fueled speculation they could be artificial. Imagine a civilization harnessing a magnetar's power as a beacon, or perhaps even as propulsion for interstellar ships. While Occam's razor favors natural explanations, the truth is stranger than fiction. We're witnessing physics at its most extreme, where matter crushes into densities so extreme a teaspoon would weigh 1 billion tons. What's certain is this: FRBs are no longer just distant anomalies. With magnetars lurking in our own galactic backyard, astronomers now have front-row seats to these cosmic fireworks. Telescopes like CHIME and FAST scan the skies around the clock, catching these ephemeral bursts in real time. Each detection peels back another layer of the mystery, whether it's the mechanics of neutron stars or just maybe something far more profound. One thing's clear: when the next FRB flashes, the whole universe will be listening. Deep in the heart of the Milky Way, where gravity twists the rules of physics, a flock of young stars orbits dangerously close to our galaxy's supermassive black hole. These shouldn't exist, not here, not like this. Stars this fresh, barely a few million years old, should never have formed in Sagittarius A's murderous grip. The tidal forces alone should shred stellar nurseries before they could take shape. Yet somehow, dozens of them whirl around the black hole at breakneck speeds, defying every expectation. The mystery thickens when you realize how they move. Unlike older stars tracing lazy ellipses, these youngsters race in tight, circular orbits like planets around a sun, but with a black hole as their anchor. Their speed is staggering, some clocking over 3 million miles per hour, fast enough to cross the United States in under 10 seconds. Conventional wisdom says gas clouds this close to a black hole would be stretched into spaghetti, not condense into stars. So how did these stellar infants survive? One compelling theory suggests they didn't form here at all. They were kidnapped. Imagine a star cluster spiraling too close to Sagittarius A, its outer stars ripped away while the core held tight. Over time, friction with surrounding gas could have dragged these survivors inward, forcing them into their current breakneck orbits. It's called forced migration, a gravitational heist orchestrated by the black hole itself. But there's a catch. Recent observations reveal some of these stars are even younger than the migration process should allow, meaning they might have formed in situ against all odds. Could dense gas disks around the black hole have shielded them during birth? Or does some unknown mechanism let stars ignite in places we thought were sterile? Every answer we uncover only deepens the puzzle. Upcoming telescopes like the Extremely Large Telescope will study these stars in unprecedented detail, probing their chemistry and motion for clues. What they find could rewrite our understanding of how stars are born, not just near black holes but everywhere in the universe. For now, these reckless youngsters keep dancing on the edge of destruction, a cosmic contradiction spinning at the heart of our galaxy. Out in the constellation Cygnus, a star named KIC 8462852, better known as Tabby's star, behaves like nothing else in the galaxy. At times, its light flickers unpredictably, dimming by up to 22% before snapping back to normal. That's not just unusual, it's downright impossible by regular stellar standards. Planets, even large ones, typically cause dips of less than 1% when they transit. So when astronomers first spotted this erratic pattern, theories exploded. Could this be evidence of an alien megastructure, something massive enough to block a star's light in such bizarre ways? But before we jump to otherworldly explanations, let's look at the facts. Detailed studies have ruled out a single solid object. Instead, the leading suspect is cosmic dust, but not the smooth, even kind. Imagine a vast, uneven cloud of fine particles, maybe debris from colliding asteroids or the remnants of a shattered planet. Infrared observations support this, showing that whatever's blocking the light isn't completely opaque but scatters some wavelengths more than others, just like dust would. Yet there's another twist. Some dips in brightness last for days, while others stretch for weeks or even months. This has led to wilder proposals, like a swarm of comets caught in an unstable orbit, breaking apart and spreading their icy fragments across the star's path. It's a scenario that could explain the irregular dimming, but even then, the sheer scale of material required pushes the limits of plausibility. The truth is, Tabby's star still defies a perfect explanation. That's why telescopes keep watching it, hunting for patterns that might finally crack the case. Every new dimming event offers fresh clues, whether it's a natural cosmic phenomenon or just maybe something even more extraordinary. For now, it remains one of the Milky Way's most mesmerizing puzzles, a reminder that sometimes the most fascinating mysteries aren't about what we know but what we still don't. Beyond the known reaches of our solar system, something massive may be lurking in the dark. A hidden world so large it tugs at the fabric of our cosmic neighborhood. Astronomers call it Planet 9, a hypothetical super-Earth up to 10 times heavier than our own, orbiting far beyond Neptune. The evidence: strange, clustered paths of icy objects in the Kuiper belt, all tilted in ways that suggest an unseen gravitational hand is herding them. Picture a cosmic shepherd, a planet so distant it takes 10 to 20,000 years to complete a single orbit around the Sun. Its existence was first proposed when researchers noticed that several extreme trans-Neptunian objects shared bizarre, elongated orbits, all pointing in the same direction. Statistically, the odds of this happening naturally were slim, less than 0.2%. Something had to be sculpting their paths, and a hidden super-Earth fit the bill perfectly. But how did it get there? One daring theory suggests it didn't form here at all. It was captured billions of years ago, when the Sun was still nestled in its birth cluster alongside other young stars. Our solar system might have stolen this rogue planet from a neighboring star. Another possibility is that Planet 9 was born much closer to the Sun, only to be flung outward by Jupiter's gravity during the chaotic early days of planetary migration. The hunt is now on to pin it down. Telescopes like Subaru in Hawaii scan the skies with cutting-edge optics, searching for the faintest glimmer of reflected sunlight. Even the Vera Rubin Observatory, set to come online soon, could spot it within its first few years of operation. But here's the twist: Planet 9 might not be alone. Some models hint at even more undiscovered worlds lurking in the frigid outskirts of our solar system, each hiding in the shadows, waiting to be found. Whether it's a captured wanderer or a relic of our own solar system's violent youth, Planet 9 challenges everything we thought we knew about our cosmic backyard. If it's real, it could rewrite the story of how planetary systems form, and remind us that even in our own neighborhood, the universe still has secrets left to reveal. At the very core of our galaxy, where stars crowd together in a swirling dance, there's something else stirring, an eerie, persistent glow that shouldn't exist. Scientists call it the galactic center excess, a mysterious flood of gamma rays radiating from the Milky Way's heart with no obvious source. Discovered by the Fermi Large Area Telescope, This energy signature defies simple explanation, flickering like a cosmic lighthouse with no keeper. One camp of researchers believes we might be witnessing dark matter's grand finale, particles of this elusive substance colliding and annihilating each other in bursts of high-energy light. If true, it would be the first direct clue to dark matter's identity, like catching a ghost in the act of vanishing. The gamma ray's specific energy range matches predictions for certain theoretical particles, adding fuel to this tantalizing idea. But there's another contender in this cosmic whodunit: pulsars. These rapidly spinning neutron stars, the dense remnants of dead suns, can also produce gamma rays as their intense magnetic fields accelerate particles to near light speed. The galactic center is packed with them, hidden within the dust and chaos. Could a previously unseen population of these stellar corpses be masquerading as dark matter's signature? Recent studies have added twists to both narratives. Some gamma-ray patterns align more closely with pulsars' expected distribution, while other features stubbornly resist explanation without invoking dark matter. The debate rages on, with each new Fermi data release scrutinized like a detective's fresh lead. What makes this mystery so compelling is its stakes. It could either unveil the nature of the universe's missing mass or reveal an entirely new aspect of stellar evolution. Upcoming instruments like the Cherenkov Telescope Array will peer deeper into this gamma-ray fog, hunting for subtle clues in its shimmering haze. Until then, the galactic center excess remains a beacon of unanswered questions, reminding us that sometimes the brightest light casts the longest shadow. For decades, NASA twin Pioneer spacecraft streaked through space as models of precision until they did something utterly inexplicable. As the probes hurtled beyond Saturn, mission controllers noticed a tiny but persistent deviation in their speed. Both spacecraft were slowing down more than physics predicted, as if an invisible hand were gently pulling them back. This slight but measurable discrepancy became known as the Pioneer anomaly, a puzzle that would haunt scientists for over 30 years. At first, whispers of radical explanation swirled. Could it be drag from unseen dark matter, or worse, a sign that Einstein's theory of gravity needed rewriting? The numbers were undeniably strange. Both probes experienced an identical deceleration equivalent to just 1/10,000,000th of Earth's gravity. Minuscule, yes, but far too consistent to ignore. Then came a breakthrough: thermal recoil. Engineers realized heat radiating unevenly from the Pioneer's power systems could create a tiny thrust effect, like a tea kettle hissing steam in reverse. When researchers painstakingly reconstructed the spacecraft's heat maps, the math suddenly aligned. Case closed, or so it seemed, yet some mysteries refused to stay solved. While thermal recoil explains most of the anomaly, a faint residue of uncertainty lingers. The precise distribution of heat doesn't account for every nuance in the data, leaving a sliver of the deceleration unaccounted for. Could there still be undiscovered physics at play? The debate remains quietly alive in academic circles, a testament to how even the smallest cosmic quirks can challenge our understanding. What makes the Pioneer anomaly so fascinating isn't just the solution. It's the reminder that space exploration is filled with hidden variables. Every mission, no matter how meticulously planned, can stumble upon the unexpected. Today's spacecraft, like New Horizons, are designed with these lessons in mind, their trajectories adjusted for the subtle push of sunlight and heat. But the Pioneer's legacy endures, a masterclass in how patience, creativity, and relentless curiosity turn anomalies into breakthroughs. Imagine a world where the very ground beneath your feet isn't rock or ice but diamond. Meet Quasar J1719-1438b, a planet so extreme it defies every expectation. Orbiting a dead star just 4,000 light-years away, this exotic world isn't just sprinkled with gemstones, it might be one, a colossal cosmic diamond forged in the aftermath of stellar catastrophe. The story begins with its host, a pulsar, the rapidly spinning corpse of a massive star that went supernova. Most pulsars don't have planets, yet here one orbits, surviving the blast that should have vaporized everything nearby. How astronomers suspect this wasn't always a planet. Billions of years ago, it might have been a white dwarf, the dense core of a star like our Sun. When the pulsar's gravity began siphoning away its companions' outer layers, what remained was crushed under unimaginable pressure, transforming its carbon into a crystalline lattice, a diamond the size of a planet. But is it really a glittering gem? The truth might be even stranger. While the conditions are perfect for crystallized carbon, the planet's surface could resemble something closer to a super-dense, metallic world, its diamond-like core shrouded under layers of degenerate matter. Temperatures here likely soar to thousands of degrees, turning any dream of mining it into pure science fiction. Yet the real wonder isn't just its composition, it's the violence that birthed it. This planet is a cosmic phoenix, a remnant of a star system torn apart and reborn as something entirely new. Future telescopes might one day analyze the light filtering through its atmosphere, if it has one searching for spectral signatures of carbon crystals. Until then, PSRJ 1719-1438b remains a dazzling enigma, proof that the universe can craft treasures far beyond our wildest imagination. In the vast tapestry of cosmic oddities, few sights are as striking or as baffling as the Red Rectangle Nebula. Hovering 2,300 light-years away in the constellation Monoceros, this geometric marvel looks like a celestial stained glass window, its crimson glow framed by an eerie, symmetrical X-shape. But don't let its artistic beauty fool you. This is a cosmic crime scene where two stars locked in a gravitational dance are slowly tearing each other apart. At the nebula's heart lies HD 44179, a binary system where an aging red giant star spills its outer layers onto a smaller, hotter companion. Normally, this would create a classic planetary nebula, a glowing shell of gas, but here something went spectacularly wrong. Instead of expanding evenly, the ejected material funneled into two cone-shaped jets, sculpted by the star's mutual orbits into that iconic X-shape we see today. Think of it like squeezing a water balloon from both ends. The pressure creates twin streams, frozen in time by the vastness of space. Then there's the color, a deep, unsettling red unlike anything else in the cosmos. Spectroscopy reveals the culprit, exotic hydrocarbons known as polycyclic aromatic hydrocarbons, or PAH. These complex molecules, more commonly found in soot or engine exhaust on Earth, are swirling through the nebula in unprecedented quantities. No one knows exactly how they formed here, but their infrared glow paints the entire structure in shades of crimson. Some scientists speculate these compounds could be the building blocks of life, forged in the turbulent winds between dying stars. Yet the red rectangle still guards its deepest secrets. Why is the X-shape so precise? How did those hydrocarbons become so abundant? Even Hubble's sharpest images can't peer deep enough to unravel the full story. Future telescopes, like the James Webb Space Telescope, might finally decode the chemistry behind this cosmic artwork, revealing whether it's a fleeting masterpiece or a signpost to something greater. For now, it stands as a testament to the universe's ability to blend destruction and beauty into one breathtaking mystery. Somewhere in the depths of the Milky Way, a cosmic predator spins at dizzying speeds, devouring its neighbor in one of the most extreme displays of celestial violence ever witnessed. Meet PSRB 1957 plus 20, better known as the Black Widow pulsar, a neutron star so lethal it's literally evaporating the star it orbits. This isn't just a simple dance of gravity, it's a death sentence. Chandra X-ray observatories' haunting images reveal the carnage. The pulsar's companion star, once a sun-like giant, now reduced to a withered husk being blasted by particle winds moving at 600 kilometers per second. These winds are so intense, they strip away material from the doomed star atom by atom, like a sandblaster carving through rock. The Black Widow earns its name from nature's deadliest spider, but this celestial version is far more terrifying. Spinning nearly 600 times a second, this pulsar bombards its partner with gamma rays and charged particles, cooking it from the outside while tidal forces tear at its core. Over millions of years, the companion will be completely vaporized, leaving behind only a ghostly trail of ionized gas, the last whispers of a star erased from existence. Yet for all its destruction, this system holds vital clues about the universe's most extreme physics. The pulsar's wind creates shockwaves that glow in X-rays, giving astronomers a rare lab to study particle acceleration at energies impossible to replicate on Earth. There's even evidence that some material from the evaporated star gets caught in the pulsar's magnetic field, fueling its deadly spin. What happens next? Eventually, the Black Widow will finish its meal, but not before teaching us how neutron stars shape their surroundings, and perhaps even how similar systems might one day trigger new cosmic explosions. Until then, it remains a chilling reminder that even in the vastness of space, annihilation can come in the smallest, most relentless forms. Towering across the cosmos like a bridge between realities, the Hercules Corona Borealis Great Wall defies everything we thought we knew about the universe's structure. This mind-bending filament of galaxies stretches an almost unimaginable 10 billion light-years, so vast it would take a beam of light twice the age of Earth just to traverse it. To put that in perspective, if our Milky Way were the size of a grain of sand, this colossus would span the length of a football field. And yet, according to our current understanding of physics, it shouldn't exist at all. Here's the cosmic rule it breaks, the cosmological principle which states that on large scales, the universe should look roughly the same in every direction. No single structure should dominate, but the Great Wall does exactly that, a sprawling, lopsided tapestry of galaxy clusters so immense it challenges the very foundations of modern cosmology. Some researchers argue it's just a statistical fluke, a chance alignment of smaller structures that appears connected from our vantage point, but the data tells a different story. Detailed 3D mappings of galaxy positions reveal the wall's eerie coherence, like finding a perfectly straight road carved through a random forest. Its galaxies share motion patterns and distances that suggest a true physical connection, not an illusion. Could this be a remnant of the universe's infancy, when quantum fluctuations in the newborn cosmos froze into place on scales we're only now beginning to see? Or does its existence hint at something even more profound, a flaw in our models of cosmic inflation? The mystery deepens when you realize the Great Wall isn't alone. It looms near the Boötes Void, that haunting cosmic desert we explored earlier, as if the universe balanced an inconceivable emptiness with an equally inconceivable density. Upcoming sky surveys like those from the Euclid Space Telescope will test whether such structures are rare exceptions, or signs that the cosmos organizes itself in ways we've yet to comprehend. Until then, this galactic leviathan stands as a humbling reminder. The universe writes its own rules, and we're only beginning to read them. Imagine if you tipped a glass of water and watched in disbelief as half of it vanished before hitting the floor. That's essentially what astronomers face when studying our own galaxy, because roughly half of the Milky Way's expected normal matter is simply missing. Not dark matter, not exotic particles, but the ordinary protons and neutrons that make up everything from stars to human bodies. This cosmic accounting error is known as the missing baryon problem, and solving it has led scientists on a hunt through the most elusive corners of space. For decades, the math was undeniable. If you tally up all the visible stars, gas, and dust in the Milky Way, it adds up to just half the baryonic matter predicted by cosmic models. So where's the rest? The leading suspect is something called the warm-hot intergalactic medium, WIM for short. Picture a vast, diffuse web of superheated gas threading between galaxies, so thin it's nearly invisible. This stuff isn't cold enough to form dense clouds, nor hot enough to glow brightly in X-rays. It's the universe's ultimate hide-and-seek champion, lurking in filaments too faint for most telescopes to spot. But recently, breakthroughs have started peeling back the veil. ESA's XMM Newton and NASA's Chandra X-ray Observatory have detected faint whispers of oxygen ions in these intergalactic tendrils, their spectral fingerprints betraying the WIM presence. Even more promising, fast radio bursts, those millisecond cosmic flashes we discussed earlier, act as natural probes. As these bursts travel through space, they interact with the WIM, leaving subtle imprints that reveal how much matter they've passed through. The implications are staggering. If confirmed, this hidden reservoir could solve not just the Milky Way's missing matter, but a universal discrepancy affecting all galaxies. Upcoming missions like Athena, set to launch in the 2030s, will scan deeper into these ghostly filaments, hunting for the faint glow of million-degree gas. What they find might finally balance the cosmic books, proving that the missing half of our galaxy wasn't gone after all, just hiding in plain sight all along. Somewhere between the stars, in the quietest stretches of space, an entire shadow ecosystem of matter waits to be discovered. And when we find it, we won't just solve a scientific mystery, we'll rewrite the inventory of the universe itself. The universe isn't just expanding, it's doing so at breakneck speed, as if some unseen force is pressing harder on the cosmic accelerator with every passing second. This startling discovery, first made in the late 1990s by observing distant supernova, upended our understanding of gravity and revealed one of the greatest mysteries in modern cosmology: dark energy. Unlike dark matter, which pulls galaxies together, dark energy pushes them apart, an anti-gravity so powerful it makes up 68% of the universe's total energy. And yet, we still don't know what it actually is. The leading theory, known as lambda CDM, treats dark energy as a constant, like a property of empty space itself. Imagine blowing up a balloon with dots on its surface. As it inflates, the dots move apart. But dark energy would be like the balloon suddenly stretching faster over time, as if the rubber grew restless. This model fits observations neatly, but it leaves a glaring question. Why does empty space have this repulsive energy at all? Enter quintessence, an exotic alternative where dark energy isn't constant but evolves, ebbing and flowing like a cosmic tide. Named after the ancient Greek fifth element, this theory proposes a dynamic field permeating the universe, one that could even interact with matter in ways we haven't detected yet. If true, it might explain why dark energy's effects seem to strengthen as the cosmos grows sparser. Type Ia supernovas serve as our cosmic lighthouses in this search. These stellar explosions always shine with the same intrinsic brightness, letting astronomers measure vast distances with precision. When researchers compared supernova billions of light years away to nearby ones, they found the distant ones fainter than expected, proof the universe's expansion wasn't slowing as once assumed but speeding up. The enigma only deepens with time. Does dark energy's strength change? Could it someday reverse, collapsing the universe in a big crunch? Upcoming projects like the Dark Energy Spectroscopic Instrument, DAISY, are mapping millions of galaxies to track expansion with unprecedented detail, while space telescopes like Euclid hunt for distortions in spacetime caused by dark energy's push. Until then, this invisible driver of cosmic destiny remains one of the Milky Ways and the universe's most profound puzzles, a reminder that even the emptiest stretches of space hold secrets we've barely begun to unravel. Hidden in the constellation Monoceros, a cosmic enigma lurks, small enough to defy classification, yet massive enough to rewrite the rules. Astronomers have nicknamed it the Unicorn, a black hole candidate so petite it barely tips the scales at 3 times the mass of our Sun. Nestled beside a crimson giant star named V723 Monocerotes, this object tugs at its companion with gravity too strong for a neutron star, yet doesn't quite fit the profile of a typical black hole. That's what makes it so fascinating. It might not be either, but something entirely new. Most black holes we've found fall into two categories: stellar mass black holes, born from collapsing stars and weighing at least 5 solar masses, or supermassive beasts anchoring galaxies. The unicorn sits stubbornly in the gap between them and neutron stars, the dense remnants of dead stars that max out around 2.5 solar masses. So which is it? Its gravitational pull distorts the red giant's shape, creating telltale brightness variations that betray its presence. But here's the catch: if it's a black hole, it's the smallest ever confirmed. If it's a neutron star, it's impossibly heavy, straining the limits of physics. Some theories suggest it could be a rare mass gap object, a missing link bridging neutron stars and black holes. Others propose it's a neutron star caught in the act of collapsing, teetering on the edge of becoming a black hole. Then there's the wild card. Could it be something more exotic, like a quark star, where matter crushes down into even stranger subatomic soup? The hunt for answers is heating up. Telescopes are now monitoring V723 MON for X-ray flares, smoking gun, evidence of a black hole's accretion disk. But if the unicorn stays quiet, it might hint at a neutron star with a stealthy magnetic field. Either way, this tiny titan proves that sometimes the universe's most revolutionary discoveries come in the smallest packages. Rising from the Milky Way's core like fiery tidal waves, two colossal jets of supercharged plasma stretch halfway across our galaxy, enough to span the distance from Earth to the Large Magellanic Cloud and back. These aren't just any cosmic eruptions, they're the galactic geysers, towering fountains of million-degree gas that defy the serene image of our home galaxy. Discovered by NASA, a Fermi gamma-ray space telescope, and later mapped in X-rays by the Rosat satellite, these structures reveal a hidden violence etched into the Milky Way's ancient past. The geyser's sheer scale is breathtaking. Each jet blasts outward for 25,000 light-years, energized by particles moving near the speed of light. But what could launch such a cataclysmic outburst? The prime suspect lies buried in our galactic center, Sagittarius A, the supermassive black hole that once roared to life as a quasar. Billions of years ago, when the Milky Way devoured more gas and stars, its black hole may have funneled infalling material into these bipolar jets, carving scars that still glow today. Yet there's another twist. ESA's Planck satellite detected these geysers not just in X-rays but in microwave light, tracing vast magnetic fields threading the plasma like cosmic wires. This suggests a second culprit: magnetic reconnection, a process where tangled magnetic fields snap and release explosive energy. Picture a rubber band stretched too tight, suddenly breaking and flinging stored power in all directions. In the galactic center, such events could accelerate particles to extreme velocities, sustaining the geysers long after their initial eruption. What makes these structures so fascinating isn't just their origin, it's their lingering impact. The geysers act like a pressure valve, regulating how energy escapes our galaxy. Some researchers think they might even seed intergalactic space with heavy elements forged in stellar explosions, spreading the ingredients for future stars and planets far beyond the Milky Way's borders. As next-generation telescopes like the upcoming Athena X-ray Observatory study these plasma fountains in greater detail, we might finally learn whether they're relics of a bygone quasar era or evidence of ongoing magnetic storms. Either way, the galactic geysers prove that even a seemingly quiet galaxy like ours hides echoes of a tempestuous youth, written in jets of fire stretching toward the void. Hubble's sharp eye recently caught something extraordinary: a supermassive black hole weighing as much as 20 million suns, racing through intergalactic space at staggering speeds. Unlike the stationary giants anchoring most galaxies, this cosmic fugitive barrels forward, trailing a shockwave of newborn stars in its wake like a celestial breadcrumb trail. The discovery marks the first solid evidence of a runaway supermassive black hole, and its story begins with one of the universe's most violent events, a galactic collision. Picture two galaxies merging, their black holes spiraling toward each other in a gravitational dance. As they draw close, a third galaxy intrudes, disrupting their orbit. In the chaos, one black hole gets hurled outward at speeds topping 4 million miles per hour, while the others recoil in the opposite direction. That's precisely what might have launched this rogue behemoth. The gas trail behind it, a cosmic contrail from the galactic disk it ripped through on its way out, compressed and ignited into a river of young blue stars. What's baffling is how anything could survive such an ejection. Supermassive black holes are thought to grow by staying put, feasting on gas and stars in their host galaxies. Yet here's one stripped of its home, forging its own path through the void. The implications are staggering. If this nomadic black hole isn't alone, there could be others lurking in the darkness, invisible until they interact with surrounding gas. Upcoming telescopes like JWST may hunt for their faint trails, rewriting our understanding of how black holes shape the cosmos. For now, this cosmic outlaw serves as a reminder. Even the universe's most anchored titans can be set adrift. Deep in the Orion Arm, one of the Milky Way's great stellar nurseries, there's a patch of darkness that shouldn't exist. Astronomers call it the mystery spot, an interstellar cloud so dense it swallows radio waves whole. Most cosmic gas clouds let light pass through, with only certain wavelengths absorbed. But this one, it acts like a cosmic sponge, soaking up an unusually wide range of radio frequencies and leaving scientists scrambling for answers. What makes this cloud so baffling is its composition. Typical interstellar dust contains simple molecules like carbon monoxide or water ice substances that absorb very specific frequencies like a fingerprint. But the mystery spot smothers signals across a much broader spectrum, suggesting it's packed with exotic molecular structures we've rarely seen. Some researchers speculate it could be teeming with complex organic molecules, perhaps even probiotic compounds that hint at the building blocks of life. Others wonder if it's hiding an unusually high concentration of metallic dust, which can scatter radio waves in unexpected ways. Then there's the location. Nestled in a region bursting with young stars, the cloud might be a cosmic pressure cooker, a place where intense radiation and shock waves from nearby supernova have forced atoms into strange new arrangements. Recent observations from the Atacama Large Millimeter Array ALMA reveal bizarre chemical signatures here, including molecules that shouldn't survive long in space unless shielded by something even more unusual. The biggest question, though, is whether this anomaly is unique. Could there be other radio dark clouds lurking undetected across the galaxy? Future telescopes like the Square Kilometer Array SCAR could scan the skies for similar shadowy patches, turning up clues about how chemistry operates in the most extreme corners of space. For now, the mystery spot keeps its secrets locked away in silence, an eerie reminder that even in well-traveled regions of the Milky Way, the universe still has tricks up its sleeve. Our Milky Way wasn't always the grand spiral we see today billions of years ago. It was a cosmic battlefield, colliding with smaller galaxies in violent mergers that left scars we can still trace. One of the most startling discoveries from the Gaia Space Telescope is the evidence of a colossal galactic wreck now nicknamed the Gaia Sausage, the remnants of a dwarf galaxy that smashed into ours so hard. Its stars still move in strange, stretched-out orbits unlike anything else in the galaxy. This ancient interloper wasn't just a passing visitor. It was massive, roughly the size of 10 billion suns. It plowed into the Milky Way's center head-on, its gravity flinging stars into wild, radial paths that resembled, well, a sausage. Gaia's precision mapping revealed thousands of these stars, all moving together in a distinct pattern, their trajectories frozen in time like a cosmic fossil record. But here's the twist. These stars aren't just oddballs in motion, they're also freakishly rich in metals. That points to a dwarf galaxy far more chemically evolved than most, likely packed with generations of supernova that forged heavier elements before the collision. Based on the orbits, astronomers estimate the merger happened around 8 to 11 billion years ago, a time when the Milky Way was still taking shape. The impact might have even helped sculpt our galaxy's thick disk, puffing it up with displaced gas and stars. What's truly remarkable is how this discovery reshapes our origin story. The Gaia sausage isn't just debris. It's evidence that the Milky Way grew by devouring smaller galaxies, each collision leaving behind a hidden fingerprint. Future data from Gaia and next-gen telescopes could uncover even more of these ghostly mergers, revealing just how violent and chaotic our galaxy's past really was. For now, those rogue stars keep looping through space, a silent testimony to the chaos that built our cosmic home. At the edge of the observable universe, where time itself seems to warp under the weight of cosmic infancy, there's a celestial paradox shining brighter than anything should at that age. Euler's J1342 plus 0928 isn't just any quasar, it's a time-traveling anomaly, a supermassive black hole so impossibly large and ancient that it defies our understanding of how such monsters could exist so soon after the Big Bang. This cosmic heavyweight tips the scales at 800 million times the mass of our Sun, yet it existed when the universe was just 5% of its current age, a mere 690 million years after creation. By all known physics, there simply shouldn't have been enough time for anything to grow that massive. Traditional models suggest black holes form from collapsing stars, gradually bulking up over billions of years by swallowing gas and merging with others. But J1342 didn't have billions of years. It had barely a fraction of that. So how did it get so big, so fast? One radical theory suggests the universe's first black holes weren't born from stars at all, but collapsed directly from dense pockets of primordial gas, leapfrogging the usual growth stages. Imagine skipping the sapling phase and sprouting a full-grown redwood overnight. Others propose these early giants gorged on ultra-dense gas flows in the chaotic young cosmos, feasting at rates far beyond what's possible today. The discovery sent shockwaves through astrophysics because it's not alone. Several other quasars from this epoch also flaunt baffling sizes, hinting that either our models are missing a crucial piece of black hole physics, or the early universe operated under entirely different rules. Telescopes like JWST are now hunting for even earlier quasars, probing the darkness for clues about how these titans could dominate the cosmic landscape almost instantly. What's at stake isn't just a tweak to the textbooks, it's a potential rewrite of cosmic history. If supermassive black holes truly formed in ways we can't yet explain, they might have shaped the entire trajectory of galaxy evolution, lighting up the universe before it was ready. And that raises an even deeper question. What other impossibilities are waiting to be uncovered in the dawn of time? For all the wonders we've uncovered in the Milky Way, one question lingers like a shadow: where is everyone? Among the galaxy's hundreds of billions of stars, with countless Earth-like planets orbiting inhabitable zones, the silence is deafening. This is the Fermi paradox in our own backyard. The glaring contradiction between the high probability of alien civilizations and the complete lack of evidence they exist. If the universe is so full of promise, why does it feel so empty? One unsettling possibility is the zoo hypothesis, the idea that advanced civilizations might be deliberately avoiding contact, observing us like animals in a cosmic wildlife preserve. It's a comforting thought in some ways, suggesting we're being spared from interference until we're ready. But then why wouldn't we at least catch stray signals? Even a cautious civilization might accidentally leak evidence of its existence, like the radio chatter we've been broadcasting for decades. The darker alternative is the Great Filter, a catastrophic hurdle so immense that almost no life survives it. Maybe the leap from simple life to intelligence is astronomically rare, with most planets stalling at bacteria. Or perhaps intelligent life tends to self-destruct through war or climate collapse before reaching the stars. If true, the silence could be a grim warning. Civilizations like ours might flicker out before ever making contact, but here's the twist: we may be searching the wrong way. Our hunt for radio signals assumes aliens communicate as we do. What if they've moved beyond radio to technologies we can't fathom, like neutrino beams or quantum entanglement? Or worse, what if we're alone not because life is impossible, but because we're the first? The Milky Way is ancient, but the conditions for complex life might have only recently aligned. The answer, if there is one, could redefine our place in the cosmos. Projects like SETI and Breakthrough Listen continue scanning the skies, while new telescopes probe exoplanet atmospheres for biosignatures. Until then, the paradox remains, a humbling reminder that the universe owes us no answers. Whether we're being watched, doomed, or simply early, the silence speaks volumes. From gamma-ray bubbles stretching across the galaxy to whispers of alien signals lost in static, the Milky Way isn't just a collection of stars, it's a cosmic hall of mysteries. We've journeyed past black holes that defy physics, through voids where galaxies vanish, and into the heart of dark matter's invisible grip. Every corner of our galaxy holds something bizarre, something unexplained, whether it's diamond planets forged from dead stars, runaway black holes racing through space, or the haunting silence of the Fermi paradox. Truth is, the universe doesn't need science fiction to be strange. The real thing is far weirder, and the best part, these 25 phenomena are just the beginning. With every telescope pointed at the sky, every orbit calculated, and every signal decoded, we peel back another layer of the Milky Way secrets, only to find more questions waiting underneath. So tell me, which mystery captivated you the most? The Great Attractor's unseen pull, the wow signal's fleeting hello, or maybe those young stars dancing recklessly around a black hole? Drop your favorite in the comments. I'd love to hear what sparks your cosmic curiosity. And if you're hungry for more deep dives into the universe's oddest corners, hit subscribe. The cosmos isn't done surprising us yet, and neither are we. Until next time, keep looking up. The next great mystery might be revealed tomorrow.